perhaps send some virtual candies. Would you like some virtual candies?
Or maybe some Bitcoin.
That's the best.
Or maybe some Bitcoin.
All right, I guess I think we are live. Can maybe someone double check if we are really live?
I
think we are live.
Yeah, we are live.
Can maybe someone double check if we are really live?
We are live.
Can hear myself many times. Yeah, please enable your camera. This is a requirement for today. Yeah, please keep it enabled until the end of the lecture for about 2 hours. Let's make sure this is really interactive session, and hopefully it will be successful since it's online. Due to the extreme weather here in Georgia, we have to move to online just for today. We will be back in the classroom for Thursday, 5:30, same time. Make sure, everyone, you enable your camera for those who joined recently.
Like somebody's not giving donuts or chocolate today.
That's SysScale. In 2 weeks or so, right?
Next week, yes.
Yeah, he's not giving next week.
No, but I mean, I'm willing to dox myself for donuts at this point. Or Bitcoin.
Yeah, please, for those who joined recently, please enable your camera. We will start soon.
Prince, you have a say into this? Into Bitcoin or a chocolate, Prince?
Bitcoin sounds.
It's going crazy day by day.
I'll take Bitcoin.
Maybe last talk will be giving car.
No. It's not about taking. It's about giving. So are you giving it or not?
Me? I don't have any. I only.
Yeah, welcome everyone. Again, as I said, due to the extreme weather, today we are moving online just for today. Hopefully on Thursday we'll be back to classroom at 5:30 as usual. For today we'll have 2 more interesting topics. Please enable your camera as soon as possible and keep it open for the entire class time. We'd like to ask everyone to participate. Feel free to enable your mic and just ask your question whenever you have one, okay? Or if you want to participate in answering questions and so on. So hopefully it will be a very successful experience. This is our first time to make it online, I believe, this semester. So let's see how it goes with a large number of people. I believe it will be really enjoyable journey. As you can see in the background of SysScale, no donuts, no chocolate for today. So Now we can start as soon as Ritesh open his camera. All right. Now, Anthony, Sunanda, everyone, you need to enable your camera. We are waiting for you, guys.
Now confirm who have all voted for the class online, yes, and then check if they are in their houses or not.
Is anyone
didn't vote yes.
GSU? Anyone in campus?
Ritesh doesn't seem to be, at least. So.
Yeah, I didn't vote yes.
How come I received 45 yes?
Yeah, but I didn't email.
Okay. Yeah, it looks like Nancy also in campus. All right. So, Nick, whenever you're ready, you can start.
All right, I'll start.
All right.
All right, let's begin. Hello, everyone. My name is Mohammed Abdullah, and with me is Nick. Today, we'll be presenting shadow preventing row hammer in DRAM with Intra-Subarray row shuffling. So this is a work by V and co-authors from Seoul National University and UIUC in Chicago and Inha University. And we'll walk you through how row hammer works, why is it still important, and how shadow defends against it. All right. So imagine this is your phone screen or your computer lock screen, and it says enter your passcode. You enter your usual code, and it just doesn't work. The password is gone. Now here's the weird part. There's no hacker, no malware, nothing weird in your logs. Everything looks exactly the same. That's what this line is about. No hacker, no malware, just physics. The only thing that changed was just some bits deep down in your memory. And that's exactly what rowhammer does. It flips bits using pure hardware behavior, not a virus. So if your password suddenly stopped and you talk with your IT, hey, my password changed, what happened? And they tell you, yeah, it was just some physics. Would you believe them? Probably not, right? So by the end of this talk, we'll see how this actually happens. Let's talk why it still matters. Why when physics breaks security. So when physics breaks, security breaks. So at the hardware level, you get charge leaks in DRAM cells that does tiny physical effect bubble into data corruption. And if the flip bits are in something like page tablets or crypto keys, you can actually break security guarantees. So instead, I exploded a software bug. Rowhammer is more like I exploded how the DRAM cells are wired and packed together. So before we talk about rowhammer inside the chip, let's zoom out and see how DRAM actually lives in the system and how it works and what it consists of. So on your screen, you should see like a DIMM chip. This green stick of memory you plug into your motherboard. So this is just a chip, and I'll show you how it works. So if we look from the side, the module has chips on both sides. The front is called rank 0, which is basically a collection of 8 DRAM chips working together, and the back is rank 1, another collection of 8 chips. Now let's zoom into one of those chips. Inside a single DRAM chip, you don't have just one big block of memory. It's also split into multiple banks. Here's a picture like shows 8 banks stacked behind each other. Each bank can be doing its own thing, which helps with parallelism. So when the controller talks to a DIMM chip, it's really talking to many chips, and inside each chip, many banks. Now let's zoom in one more step into bank 0, for example.
Video eating.
Excuse me? Okay. All right. So a bank is organized as a big grid of rows and columns. Across the top, you can see something like 2 KB rows width, and along the side, you have thousands of rows. At the bottom is blue. In the blue is the row buffer. When we activate a row, the entire row is copied into the row buffer. All reads and write happen from the buffer, not directly from the cells. That detail matter because rowhammer is basically about activating certain rows over and over, which keeps stressing nearby rows in the grid. So now let's talk about what is row hammer. So we already see this hierarchy DRAM. So we first have channels, then rank, then bank, and subarrays, and finally rows. So just quickly look at this picture of rows. So type in chat, what do you guys think are where the bit flip happens? Is it green or red? Let's see. What do you guys think? Just type in the chat,
Red.
green or red.
Right.
Red.
All right. Yeah, that's right. In this particular example, it is red. So the aggressor rows are on top of them, or one below it. So the rows in green are aggressor rows, and the victim is in red. So this could be actually any of them. The aggressor could be in the middle and could do a bit flip on top or one below. So DRAM stores data in like rows of capacitor cells, and cells are packed extremely close to each other. And then when repeated activation happens, it causes electrical interference in neighboring rows, and then it causes a bit flip. So the row hammer effect. Like this slide summarizes the row hammer effect. You hammer an aggressor row with many activation. That pulls an electrical stress on the neighboring victim row. After enough hammering, some cells in the victim row lose or gain charge and flip. Modern attacks like automate this to flip specific bit insensitive structure like page tables or credentials, and then eventually you lose a security that makes your change your password or stuff like that. So let's talk about like real world examples from like phones to data centers. So this isn't just a cute lab demo. Rowhammer has been used on phones to gain access to your root Android, and it's a serious concern for servers, virtual machines, and data centers. Even though vendors added defense like TRR, new attacks like TR-RISPAS and half-table still bypass those defenses on some modules. So this is our problem statement why rowhammer still matters. The core issue is scaling. As DRAM cells shrink, they store less charge and become more sensitive. So it takes fewer activation to cause a bit flip. Existing defenses often rely on static thresholds and extra refreshes, or they track hard rows with custom SRAM CAM structures. Those can either be bypassable or too expensive at large scale. So problem we're tackling is, can we build a low overhead in DRAM defense that blocks rowhammer without huge tracking tables or crazy power costs? So as I said before, like DRAM scales, as we're scaling DRAM, the charge becoming lower, which means there are easier bit flips. And if there are easier bit flips, that means there's a larger security threat, and then we need a new defense. So let's go over a quick overview of what this paper is about. So first, rowhammer creates a bit flip that breaks both reliability and security. Second, prior solution track activation or refresh neighbors, which adds hardware cost and can miss newer attack patterns. Third, shadows idea is to shuffle rows inside each subarray using DDR5's refresh management commands, RFM. So attacker visible addresses don't stay bound to fixed physical neighbors. And finally, shadow achieves like low bit flip probability with less than 3% performance loss and less than 1% area overhead. With that picture in mind, I'll hand over to Nick to walk you through what people tried before shadow was introduced.
Thanks, Abdullah. Now that we have known the problem, let's look at what people tried before shadow. First, in DRAM solutions, like PARA, TRR, PRO-TRR, they live inside the DRAM chip and usually try to refresh nearby rows, which they detect something suspicious. Second, memory controller solutions like Blockhammer, Hydra, and Graphene. This sit in the controller, count activations, and throttle or refresh when a row looks too hot. Third, row shuffling. Approaches like RRS, which remap rows to break adjacency, but often with extra hardware costs or limitations. We'll go through a few concrete examples of these and see where they fall short. First up is PARA, probabilistic adjacent row activation. The idea is very simple. Every time you activate a row with a small probability P, you also refresh its neighboring rows. No big tables, just a random chance to repair neighbors before they flip. That's nice, because it's a stateless and hardware-like. But to be safe, P has to be high enough, which means lots of extra refreshes and noticeable power head. And PARA protects mainly direct neighbors. More advanced patterns that hammer multiple rows further apart or across boundaries can still slip through. Next is TRR, Target Row Refresh, which many vendors ship. DRAM tracks which rows are getting lots of activations. If a row crosses some internal threshold, TRR automatically refreshes its neighbors. There are two big problems. The algorithms are vendor-specific and opaque, so researchers can't easily verify them. New attacks like TRR passes and half double have shown that TRR can still be bypassed on some modules. So even with TRR turned on, rowhammer is not solved. Now, in the next slide, we'll see the memory controller side, blockhammer, Hydra, and graphene. Blockhammer monitors activation patterns and throttles access to heavy hammer rows. Hydra uses hierarchical counters global per bank and per row to detect overly hot regions and then reacts with throttling or refresh. Graphene looks a hot row table, tracking a small set of very active rows and refreshing their neighbors. If you had to implement one of these in hardware, which sounds simpler, you guys can type BH for blockhammer, HY for Hydra, or G for graphene in the chat. Yep, the common theme across all three, they all count activations and then respond. Interestingly, there's a lot of love for Blackhammer. So, why do these defenses still fail? First, they rely on static refresh or counting. But rowhammer patterns keep evolving, and clever attackers can shape accesses to dodge thresholds. Second, they often need extra SRAM or CAM to track hot rows, which doesn't scale as well as DRAM sizes grow. Third, software-style TRR emulation is reactive. It tries to patch things after the pattern is observed, instead of addressing the underlying cause. Shadow takes a different approach. Instead of just counting hammers, it moves the target. On the next slide, here's a shadow in one slide. The idea is to randomize mapping from logical rows to physical rows inside each subarray. So the neighbor of a logical row is no longer fixed. The mechanism, shadow periodically shuffles rows within a subarray using DDR5's RFM commands. On the hardware side, each subarray gets a remapping row, a small RNG, and some shuffle control logic. The outcome? The adjacency relationships attackers rely on keep changing. You have a huge counter tables, and you stay DDR5 compliant. On the next slide, it zooms in on one of the intra-subarray row shuffling. When Shadow decides to shuffle, it picks a target row inside the subarray and swaps the contents of the aggressor row with that target. The remapping row records which logical row now lives at which physical location. From the attacker's view, the addresses they are hammering keep moving around. So it's extremely hard to keep a reliable aggressor-victim pair. So as you can see, we have the three concept as well as how it works and effects for this slide. And on the next one, here's the hardware view. We have a memory controller that issues standard DDR5 commands like RFM. Inside each DRAM subarray, we have a shadow controller, an RNG unit, a remapping row, and a row copy circuit for fast in-RAM copies. The nice part, all of this sits inside the DRAM chip. The memory controller doesn't need a new interface. It just uses the existing RFM commands.
Is there a new command that does that?
No. So basically, it's the old command that's automatically generating.
Yes, so
Okay, so
Shadow doesn't introduce any new commands. It reused the existing DDR5 refresh management system for the command set, so it stays fully compliant with the standard.
okay, so now we can move to the next slide. Operationally, it works like this. For normal ACT command, Shadow looks up the remapping row and finds the correct physical row, activates the row, and increments an ACT counter for this logical row. When an RFM command arrives, Shadow can trigger a shuffle. It queries the remapping row, chooses a new target row via the RNG, copies data, and updates the mapping entry. So instead of a big global hot row table, everything is handled locally inside the subarray. And for the overflow step-by-step process of shuffle process, we can see it goes from trigger, selection, transfer, remap, and then refresh and reset. The process goes from MC scheduler, ACT issues, and then gradually moves to increment counter or query remapping row, or from there it goes to activate target row. As you can see, the increment ACT counter on the other hand goes from RAM IMT, if it's flagged, RFM issues, incremental refresh, or query remapping row. And then finally, the shuffle row or update remapping row. Okay, so on the next slide, we'll see why it's DDR5 compliant. One key selling point is DDR5 compliance. Shadow only uses existing RFM commands. It doesn't require new opcodes or timing parameters. It doesn't touch TRCD, TRS, or TREFI, etc. So the memory controller timing model stays the same. From the outside, a shadow-enabled module just looks like DDR5 that mysteriously doesn't suffer from row hammer. And that's exactly what vendors want. With the mechanism in place, I'll hand it back to Abdullah to look at how they evaluated Shadow.
Thanks, Nick. So now let's talk about how they actually evaluated Shadow. So on the far left under the system overview, they're using cycle-accurate emulator simulator. That means every DRAM command and timing constraint is modeled at clock cycle granularity, not just approximated. The workloads that they feed into the simulator come from SPEC CPU plus synthetic row hammer tests. So they never cover both normal programs and worst case hammer patterns. For workloads, they use, and for moving one step ahead, we have simulation environments. So here they plug in DDR5 like DRAMs with paired subarrays and the shadow logic inside of the DRAM chips. They evaluated it under both single bank and multi-bank access patterns. So they are not just cherry picking an easy case. This log is also responsible for recording bit flips, latency, and area overhead. And they use fault injections to model reliability. Basically, they deliberately inject row hammer style faults to see how often Shadow lets something slip through. And now in the middle column, we have 3 green boxes: workload module, defense module, and measurement module. The workload module generates a mix of standard and hammer style memory patterns. It also tracks ACT and REF commands, so the access timing is realistic, not just random reads and writes. And then we have defense module is where they plug in Shadow. It implements shadows in DRAM shuffle plus remap logic, and then triggers shuffle using RFM commands, all without extra CPU overhead. Then the comparison runs, they swap shadow out and plug in para, TRR like schemas or RS here. Then the measurement module is the stats engine. It logs how many bit flips happen, how much performance slowdown each defense introduces, and what the area power overhead would be if you actually build this in a silicon chip. On the right hand side, we have comparative baseline and output and validation. Under the comparative baseline, they ran shadow and all other defenses like TRR, RRS, para, and other ones under the same DDR5 parameters. That way, like, the differences in results came from the defense, not just from different memory configuration. Finally, the output and validation summarizes that it was less than 3% performance loss, less than 1% area overhead, and the bit flip rate below 10 raised to power minus 12 per year. So that's basically negligible. So this pipeline gives them a control way to compare shadow fairly against other techniques. Now, what we know how the experiments are set up. So let's move to the next slide and see what the bit flip probably looks like if we compare it with other defenses. So with shadow, the bit flip drops to less than 10 to raised to power minus 12 per year. This is effectively unhammerable in practice compared to prior defenses. You get orders of magnitude fewer flips because attackers can keep a stable aggressor-victim relationship long enough to accumulate damage. So this graph presents everything and in comparison with other defenses. Now, if we move on to the performance and overhead, now if we look at performance like cross aspect workloads, shadow adds under less than 3% performance overhead compared with the baseline, and which is basically negligible almost. You wouldn't possibly be noticing a 3% performance loss. Shuffles are relatively rare, even compared to normal accesses. So most of the time, the system behaves like standard DDR5 RAM. So if we talk about latency, and it also covers the power and energy. So because shadow avoids constant neighbor refreshes and instead uses occasional shuffles, the dynamic power overhead is lower than schemes like para and other TRR or blockhammer that like use aggressively. This works on aggressive refreshing system. So we get like a strong protection without using DRAM into a refresh strong machine. And if we look at area overhead, each subarray only needs one remapping row plus small logic for shadow that keeps the area cost under 1%. That's much cheaper than having an SRAM or cap tables in the controller to track hot rows for every bank and row. So across security, performance, power, and area, shadow looks like a good hardware trade-off. Now let's talk about what strengths it has. So it's a root cause defense. It breaks predictable urgency instead of just counting hammers. It's a fully in DRAM and self-managed solution, so no CPU and controller changes are needed. It's a DDR5 compliant, making it realistic for vendors, and it provides a very low bit flip rates with modest performance and area overhead loss. So if you're designing future DRAM, these are the main strong selling points to include shadow in your DRAM for security and preventing bit flips. Now we'll talk about the weaknesses. Shadow assumes the DDR5 with RFM, so it doesn't directly retrofit to older DDR3 or DDR4 systems. It adds extra design complexity inside the DRAM, so vendors have to validate shuffle logic and remapping correctly for all the corner cases. In theory, very pathological workloads might interact oddly with frequent shuffles, even though the simulation don't show major issues. So it's not a free lunch, but the trade-offs still look reasonable, and it could still impact in a broader scheme and bigger systems, and could help. So let's look at the summary table. So there's no perfect winner. This table like lines up all the defenses we talked about: para, TRR, controller-based schemas, simple schemes, simple row shuffling, and shadow. So para is a simple but power-hungry. TRR is widely deployed but still bypassable, and controller-based schemes are strong but expensive and complex. And the static reshuffling, like RRS, helps only until an attacker learns the mapping. So Shadow is a sweet spot. It has low hardware costs, it's fully in DRAM solution, and it's dynamic randomized agency, so the target keeps moving, and the attacker can't just predict where the attack's going to be. So there's no perfect winner. However, Shadow offers a very balanced trade-off with its low power head and low performance impact, and low implementation cost as well. With that, I'll hand back to Nick to wrap up why Shadow works conceptually and where we can go next.
Thanks, Abdullah. So why does Shadow work better than traditional counter-based defenses? Most previous defenses fight the symptoms. They watch for high activation counts and then refreshes or throttle. Shadow instead changes the game board by constantly randomizing which rows are neighbors. If you can't reliably know who your neighbor is, your carefully crafted row hammer pattern becomes statistically useless. As you can see, we have the autonomous and adaptive, physics-aligned design, balanced by design, and root cause fixes, as all mentioned. Now, moving over to the next slide, the authors also sketch some future directions. First, tuning the shuffling policy. For example, adapting shuffle frequency to workload behavior or error models. Second, exploring shadow-like ideas for other memories like HBM or emerging non-volatile memories. Third, combining shadow with ECC to further reduce the probability that any flip becomes visible to software. Okay, so if we try to bring shadow-style randomization into GPU memory or HBM, what do you think the biggest challenge would be? Feel free to drop one word in chat like bandwidth, timing, or vendor control. Okay, so the answer is like all of them, like bandwidth, timing, or vendor control are some of the biggest challenges. Okay, so in the next slide, we'll be looking into them from okay, so GPUs for memories faster switching be challenging. Yeah, that's actually a good point. We'll cover that in this next page in the slide. So for security and reliability implications, from a security perspective, Shadow makes targeted row hammer attacks extremely unlikely to succeed. Attackers can still hammer, but their chance of consistently hitting the same victim rows plummets. From a reliability standpoint, Shadow keeps the bit flip rate relatively low, even as DRAM scales down. And because the defense is inside DRAM, it reduces the attack surface tied to firmware. Okay. Am I audible now?
Yeah.
You're good.
Oh, okay. Okay. Even as DRAM scales down. So, and because the defense is inside DRAM, it reduces the attack surface tied to firmware or memory controller bugs. So how Shadow enhances DRAM protection and long-term data integrity. So Rowhammer has immunity, and then the bit flip containment, fault-tolerant behavior, predictable reliability, and then low system attack surfaces. So now, you can go to the next slide. Okay, so let's think. This slide is more reflective. If Rowhammer evolves again, how might Shadow evolve with it? For example, could we add more dimensions of randomness or adapt the shuffle rules? Or could we apply similar ideas to other layers, like cache index, randomization, or SSD, wear leveling as a security feature? And more broadly, how much randomness at the hardware level do we want versus using mostly software level tricks like ASLR? Okay, so let's do a quick pulse check, by the way. You guys can write down, type down HW in chat if you think the hardware level randomness is the future, or SW if you think software randomization is enough for most cases. I think Naeem's point is actually something what I would also like assume is correct. That's actually what when we are looking through all the other research papers came up, like today's world is, yeah, it's software, but the future
Last
might
talk,
be more hardware.
yeah, Princess Talks was talking about how security can be attacked or can be addressed in software firmware world, right? That's quite easy to, I think, achieve, and then getting to hardware will be difficult because given number of OEMs and this, of course, the randomness in the workload, hopefully that may not be feasible.
Mhm. I mean, that's also a good point. Like, we also have to look like how much hardware is like efficient, the efficiency of it, like how much the companies are gonna trim their budgets and stuff. So that all depends.
Mhm.
Okay, so let's move on to the next slide, where we'll be recapping key takeaways. So rowhammer is a physics-based attack that flips bits by repeatedly activating DRAM rows. Traditional defenses rely on counting and refreshing, which are either costly, bypassable, or both. Shadow attacks the root cause, predictable adjacency, by randomizing row mapping inside subarrays using DDR5 RFM. It achieves very low bit flip probabilities with small performance, power, and area overheads. It's fully in DRAM and DDR5 compliant, which makes it practical for real hardware vendors. Now, moving on to the bigger picture, let's talk about hardware security and system security. Stepping back from Shadow specifically, here's the bigger message. When the hardware layer is vulnerable, there's only so much software can do. You can add mitigations, but you are still standing on shaky ground. Rowhammer shows that transistor level behavior can break system level security. So designing future systems means thinking about security and physics together, not a separate topic. So it's pretty close to what we discussed, like that for now, maybe softwares are doing the work, but in future, hardware and software both side by side will be the go-to. And moving on to the next slide. Okay, so we started with one bit silently betraying us and flipping under pressure. Shadow tries to flip the story. Instead of bits being passive victims, the way we arrange and move them becomes part of the defense. If we design memory to be adaptive and randomized, then simple repetitive patterns like rowhammer lose their power. So once a single bit turned against us, today every bit stands guard. What began as a breach became a lesson that resilience is not just in code, but in design. Thank you so much. That's all from us. Thank you so much for staying with us. If you have any questions about rowhammer, Shadow, or hardware security in general, feel free to let us know. We can discuss.
Yeah, we'll take questions now.
So I have a quick question, right? So if Shadow is essentially so effective, why don't we already see it in DDR5 chips?
Yeah, that's a great question. So the main thing is timing. Shadow is still like a research state prototype. DRAM vendors like move slowly because adding new logic means requalifying the chip design and like making sure it works, it doesn't break, and we have like GE deck specs. And like the good news is the Shadow is fully DDR5 compliant. So once vendors start experimenting it with RFM based design, for example, it could actually be integrated with without any major controller changes. So it's mainly on vendors when they decide to actually test it out and implement in their designs and chips.
All right, sweet. Thanks.
So on the physics part, right? I think you've already spoken about it. Is it part of the randomness that we generate today, looking at how dynamics works there, or how Shadow have looked up physics part into entire system design, right?
So it's basically just a random reshuffling of the rows. So once like the static charge comes in, it doesn't like affect that row, because it could be any row that the row hammer is attacking. So it doesn't matter. Does that answer your question?
Still, I think I'm still trying to understand how the was it related to how charge and discharge of the transistor itself have been taken place when we refresh.
I mean, adding to that, like future designs like DDR6 or HBM could replace or complement like pseudo-random logic with true physical randomness. Like even though like randomness isn't drawn from analog noise, DRAM's physical behavior is what like makes randomization effective. In Shadow, like the randomization used for Intra-Subarray row is like digitally generated, not like quantum or like physical noise, to be honest. So like Shadow's randomness is like more algorithmic, but it operates on top of the physics that causes row hammer. So physics is like the battlefield and randomness is the camouflage.
Okay.
I have a question. How is shadow different from regular row shuffling?
So like exactly both are randomized, but the timing and the scope are different. Like the row shuffling or static shuffling only happens once at the boot. So when you boot up your system, that's only what happens. So an attacker can like actually profile it and still find you the neighboring rows and can attack and cause a security vulnerability. So Shadow, on the other hand, reshuffles dynamically while the system is still running using the RFM system we talked about. And so that constant movement breaks the attacker's assumption of like fixed agency, and it's what like makes the Shadow a better, much harder security system to bypass.
I mean, adding to that, like I think classic row shuffling would like stall the bus during like the swap, whereas like in Shadow, like happens fully inside the DRAM during refresh. So yeah.
And 3% is that from the Ramulator, right? Not the actual implementation. It's all the
Correct.
simulation.
Yes, that's from the simulation.
Yes.
We'll have friction over there also. A bit of.
Yeah.
Any more questions?
Okay.
Yeah, we still have time for a question. We can take more.
If nobody has question right now, I just want to mention at the end of this meeting, please send your attendance or absence, anything for waive the absence. Please email only to my student email. Also, each group member must have their own individual annotated paper. And please, the entire group, send all required files together in one email to me. Thank you.
Thanks, Sapar.
You just like advertisements between two video clips.
I think we were flooding your inbox, right?
Yeah.
So, Nick, what do you mean by autonomous operation in Shadow?
Sorry?
So, in one of the slides, you have as benefit for Shadow that has autonomous operation. What do you mean by that?
I think it's on the left. Yeah. Go to the previous slide.
What's this one?
Anyway,
Autonomous
yeah.
operation.
Yeah. Okay. So basically, it refers to like shadow, like how the shadow like breaks the predictable like visible mapping between like logical and physical DRAM rows, like without revealing the new mapping to any external observer, like maybe like the hardware, like like the CPU or OS or like even the attacker.
How about the memory controller? Does it know about the internals of the DRAM, for example?
Does the memory controller?
Aware about
No.
the structure or the mechanism of Shadow inside the DRAM?
I would assume like no, because the memory controller like doesn't have to know about the internal like shadow structure. Like that's the main reason why we are banking on this one more than the others.
So it's not controlled by any command from memory controller?
No,
Uh,
it's not.
it's not. I mean, like it's more like sending like signals, like which can be read it by itself and doesn't have to like rely on like the hardware to directly connect to it.
Okay. What do you think, Abdullah?
Yeah, like so when the memory control like issues like commands like ACT or RFM, the shadow logic just takes over within the DRAM to like execute its remapping and like shuffle sequences without needing for any awareness or cooperation from the external memory controller.
That sounds great. We can take one more question. As a reminder, please enable your camera, keep it open for the entire class time. And those who joined recently, please enable your camera. Yeah, likewise, as we asked in the previous meetings, do you think those security attacks would be solved as we move with the technology, like moving with smaller transistor, larger memories? We have DDR5, soon we'll have DDR6, and so on.
Definitely not, because like attacks can evolve as well. And as we like said before, as the DRAM is scaling, the charge it's lowering, so there's more chance for a bit flip. So it's far from like totally solved, or so they can like get away with it.
What do you
There's
think?
still a problem at large.
I mean, in the security state, like shadow is like an anonymizing like barrier. It randomizes like physical relationships, remove deterministic attack vectors. So there's like chances, but it's totally explorable still.
And I'm surprised for good how the row hammer didn't come into picture since years of computing, right? If we look at it, I think speaking to more speakers, looking like more threatening going forward, looking at we're stacking memories and everything else on the processing in memory. Look at the correction of the data now at that point, right? I have no idea about where are we heading, I think.
Yeah.
Yeah, totally makes sense, yeah, because the attacks are evolving and there's new security vulnerabilities every new day. Like, so as with AI, it's even more like easier now to exploit a large language model and create a new attack. So we need to like start rethinking everything.
I mean, like from adding to that, like DRAM, like, scaling like broke the independent cell assumption. When TRR came into the forefront, like it was a vendor secret, inconsistent, and easy to bypass. And then as we went to like advanced attacks, like Rowhammer stopped being a single attack vector. And like still no scalable, like low overhead JDC like compliant solution. So yeah, it's a breakthrough still.
So there is a very recent white paper from NVIDIA. It's already on archive. I think they published it today, just a few hours ago. It's tried to rechange the memory architecture for LLMs. It's a very interesting paper. I would recommend everyone to read it. I will have it in the chat. Maybe. Yeah, please try to read it in your free time. Those kind of papers will really put you up to date with what's happening in industry. Not necessarily to see the changes right away. You could see it in the next few months, next 1 hour, next maybe 1 minute. We don't know. Normally, they've been working for this for a very long time, and then they release it to public. But I believe the change will come anyway to the memory architecture, because we already scale it to a point where we cannot fit more memory cells. And we cannot scale to smaller than 1 nanometer for the transistor. And people are been looking for different ways since very long time. They moved to 3D stacking, for example, to solve that issue. They might be moving to different memory technology rather than DRAM or SRAM. And this is very active topic, especially with LLM these days.
Yeah.
And even
It has
with
been like a trend.
Yeah, it is. It is. Even with Rowhammer, day by day, we start seeing attacks to different hardware platforms, including GPUs, mobile devices. It's not necessarily the DRAM for computers. So you will see it very often as we move with the scaling. All right, guys. Yeah, that was great, Nick and Abdullah.
Thank you.
All right, I believe we can take 5 minutes break, and then we'll be back for the next talk. Next presenters, please start sharing your screen. I'm not sure if the audience want to share for the first presenters. Virtually, you can make them real. All right, so we'll be back in about 5 minutes. It looks like there's an issue with sharing the screen. Or this is because the toolbox at the top Can you try to hide it? The zoom toolbox at the top of the screen. You go to more, and then you'll see hide floating panel. I think that was great. Looks good. All right, so we'll be back very soon. All right, I guess we can start now. So continue with another topic called SysScale. So Ravi, whenever you're ready, you can start. I think you are muted. Can you hear Rav? Cannot hear him. Can anyone hear him? No? Ravi? I guess you are muted. All right. So everyone, please enable your camera. Keep it enabled until the end of the lecture for today. So maybe, Tarun, you can share your screen. I'm not sure if Ravi can join by phone and speak. Oh, Ravi's here. Can you hear us? Yeah, I guess you can join from your phone. Yeah, I'll send you here in the chat. Maybe you can. Yeah, please call this number and then you can join as a phone call. Then maybe you can speak. Why I am sitting in the middle?
I'll tile it correctly. You will be hammered now.
Hello?
Oh, hi. Yes, we can hear you now.
Okay, yeah. So I'm
Uh,
using two devices, so don't mind. I don't know what to say.
oh, that's great. That's great. We can hear you very well. Tarun, maybe you can
Okay.
share your screen. Maybe you can see the slide. Let's see
Try
if we can
to
illustrate it
share the
well.
screen from my device.
Oh, yeah. Yeah, go ahead. Go ahead if you can.
Yeah. Just give me a minute.
Let's do it quickly, please.
Yeah. So I think let me hide this one. So is it okay now?
Yes, yes. I think you can start. Go ahead.
Okay. I just see the phone. Okay, yeah. So yeah, hi everyone. Sorry for the delay. So today we are going to discuss with the paper regarding SysScale, which is like try to explain how we implemented a multi-domain dynamic voltage and frequency scaling application and how it enabled for the energy efficiency. And for a notable point, so one of the authors for this paper is our professor, Dr. Alser. So just want to make a note, and if you're interested, you can go and read the paper as well. So yeah, we'll start first to try to understand what are the key concepts here and how does it goes. So yeah, can anyone seeing this picture can let us know what it is?
Processor starter.
Yeah, so it's like a CPU. So it's a processing unit where it try to run an algorithms. So this is one of the important domain in this paper. Now, considering this one, can you try to identify in a real world which is similar to CPU? Maybe in human body or anyway, something related to CPU, which will try to do the same job as CPU.
Brain.
Right. It's a brain. So so what are the CPU does to try to, run the algorithms and try to process something? Our brain also does same thing. And what is common thing between both of them? Maybe to function.
Energy.
Yes, right. So CPU requires energy and our brain requires same as food to try to, get the calories and try to function as a brain. So they are both are similar kind of working the same jobs. So it's like a human brain which do the processes, make decisions, and consumes energy to do their functions. Then we'll go to the second component of this paper, and those are input output devices. These are plain straight away, like you give some input through some input devices, like there are so many input devices right now, and we try to see like their effect as well, because based on the input devices how something going to change with respect to performance. But yeah, something is input and something is output. Similarly, similar to as sense organs, just like sense organs, how they use energy, we try to like we need energy to give to these sense organs and try to work something we want to do, the work that we want to do basically, or try to display our efforts or energy. And then the third component in this paper is important is this one. And what is this? Can anyone have any ideas?
Is that a model?
Model? I mean, what model you're saying? I mean, something related to Intel, yeah, but what component?
CPU. Processors.
We are done with that one. So the other one, the important one in like system, not in computer.
Networking chip. Network.
Mm-hmm. You know, something with CPU, input output. Then what is the last missing part to make it as a microprocessor? Memory unit. Yeah, memory controller. That's true. Yeah. So it's like a memory controller Intel version where it will inside consisting of a DRAM So this is in parallel. We can think it as a LSTM memory, where we'll try to store our childhood memories or day-to-day memories, anything. So both are related. So where we try to give some needed information to CPU and make it work. So that's like, there's a comparison that I'm drawing with respect to how the microprocessor works with the components of memory, CPU, input output, and how the task going to be done. Now we'll try to understand the real world effects if someone is using more energy, or someone is using the energy that it consists, but some other part is not using it. So one thing is stress. You'll get stress, or else you won't have let's say you have necessary energy to write an exam with your hands, but your brain is not working. For some other scenarios, like let's say you don't eat some food at night, or you miss the food, or you like me, you watch so much of comics or videos late night, and then you did not write exam. So some other ways, your brain is not working. Your brain is not brain basically. So that's one thing. And the other thing is bad memories. You forgot something. Your memory is not able to remember something. You lose something because of some changes happened with you, like something you saw, and something you watched the movie and you forgot exam, and then you try to forget like how it was happened. So some scenarios related to that, because it depends on how your energy consuming it. So if you want to use more on the input output devices and your brain is not braining it all, so these are kind of issues in real world we face in day-to-day life basis, where we have some energy on our input output devices with hands, eyes, and tongues, but the brain is not braining, or the memory you're not able to remember. So we just want to display in a real world scenario what happens for that, and we try to see how it is happening in the uh, memory and with these three domains specifically. And if we can able to manage everything perfectly, and if we try to balance our energy with respect to these D domains, we'll become like 100% brain utilization person. So we want to achieve the same thing in computer domain as well. So that's what this paper about, and we try to see like how they are able to achieve this part through efficient memory energy conversion, and how they're able to work this with through all components. So we try to go with executive summary. So what the paper is about. So by this you can get the ideas, saying that how we can able to work efficiently with all these components. So the problem they try to address here is they have identified where the power that is getting distributed with these three components is fixed power. So the memory component, let's say you can say like the memory, and the other thing is like with respect to input output, they have fixed power allocation, and due to this they facing some inefficiency because they can't able to convert the excess power they transfer into these domains to the other domains, that is compute domain. So that is the problem they have identified, and the goal is to try to develop a coordinated multi-domain. That means you try to implement some algorithm in each different domains, and that should be coordinated between them, so that they try to ask what they want, or they need to reject, they don't want extra, and the rejected one should transfer to the one which needed more. So that is what a coordinated multi-domain, that is dynamic voltage frequency scaling. So we try to learn about what this actually is, and that like how they try to adjust this voltage, voltage energy changes frequency across compute, input output, and memory domain. So we mostly target only these three domains, and we try to see like how voltage is fixed allocated to input output and memory, and how we try to transfer this to compute domain. And so sorry, the next one is motivation. So why they need to do this, and how they absorb this fixed memory allocation, and what happens when they try to change changing of frequency of voltage to memory and input output, and what they observed with respect to compute domain, how it is performing well or not. So they want to understand the like actual problem. They try to make changes and try to see like what they get. And then the last one is evaluation. So on a quick high note, so what they achieve is, so they try to improve the performance of the CPU without any like energy degradation. So they want to have the same energy, or they want to save some energy but improve the performance, and at least, and they want to decrease the consumption of energy, because like because of fixed allocation of input, output, and memory domains, they want to consume to the compute power and try to increase the performance. So that they want to achieve. And on overall scale, they try to improve the performance by 16%, and they reduce the important factor, they reduce the power consumption by 10.07%. So yeah, this is what complete about the paper, and we'll go each component in depth and try to understand how they got achieved. So this is like overall the presentation outline. So when we try to, on the most part, we try to discuss about the architecture, that too, like how the three components are, try to talk in between them during the execution process, with seek some pick and diagrams, and try to see the evaluation and result section. So yeah, we try to understand the overview of what is the system on chip architecture and how it actually coupled with these three domains. So we took the reference from this original paper itself. So we don't want to to give the much idea, which is helpful for the further rest of the paper we design. So first we have a system which consisting of compute domain, which consisting of CPU, last level cache, and graphics engine. And then we have memory driven, which consists of memory controller, which have digital version and analog version, and then DRAM, which basically converts the incoming set of instruction to bits and then try to store in the DRAMs. So that's what we have, digital and analog, which converts the basic algorithm instructions to the bits process, I mean voltage process. And then we have input output, where we have interconnect, which is connect to memory domain and then CPU domain. And then we have engine controllers, which directly talk to the peripherals. So these are the three domains that consisting of system on chip. And then we have some voltage regulators connected to each domain, and also for across the domains. So for voltage domain, which connected to is VDDQ. So basically, these two components are share the same voltage. That means they run in the same phase or same cycle. So when you try to pass the same energy, so they need to set their frequency. We try to see like how they try to set the frequency using MRC memory reference codes. But remember that DRAM and DRAM analog, it should have the same frequency, and so that same voltage need to pass to this to devices. And then there is a shared memory between shared voltage regulators between input output and then DDR or digital, because as I mentioned, if we try to convert the incoming instructions into the voltage signals, so that's why they should be in the same phase. So when they're sending, it's supposed to be received, so that voltage IO is always in the same phase. And then we have system agent, where if you try to connect with multiple components, basically with memory controller to try to receive that and send the information between the components, and then it will try to act between interconnect, communicate with the CPU as well, and then engine controllers. And then we have separate regulators, voltage regulators for CPU and last level cache, and then graphic have separate voltage. So the way they get the power is like the way that we send the power is always different, because the components which are communicated should perform in the same same phase, so that they should have same frequency of voltage. And some of them have different voltage regulators, so that they will try to work in their own phase. So we need to have a coordinated system where it should able to talk with in the different domains and gives energy efficiency. That's the overall goal of this one. So we'll try to go to the introduction part. So I just quickly cover what are the components present in it, and then how we need to proceed. So on the basic definition, a mobile microprocessor is a system on chip which designed specifically for battery powered thermally constant device. Thermally constant is very important. The second point that basically says, so whenever you say that a microprocessor is working on a thermally constant environment, that means it's supposed to take only some limit amount of power. Let's say, for example, you can say like 4.5 watts of TDP. That means you can able to consume at worst or highest running state, you can able to consume 4.5 watts. So it's supposed to emit that much of energy. So that's one thing we need to make sure. The mobile devices mostly consider thermally designed power because of the battery consumption they try to take. So that is one of the scenario that we'll try to see the real world scenarios as well. We added the scenario, so where you try to see these scenarios. So yeah, one thermal design power is one we need to implement. And the next one is power management. So if you want to make all these domains work under thermal domain, that to fixed amount of energy that's supposed to take in the high usage, there is a unit called power management unit. Power management is the one which try to use power budget algorithm to try to see how much amount of voltage that I need to send to a domain at a particular scenario. Previously, like before the SysScale, the problem is it will always have the power management unit pass fixed amount of power to these domains using power budget algorithm. So based on the problem that we identify, we need to supposed to change in power budget algorithm. So we try to we are just introducing the terms what we have here. So power management unit is the one which try to act upon to pass the voltage to certain domains based on the power budget algorithm recommendations, and we need to make sure that no device should cross their TDP, thermal design power. So that's the second other important thing. Then we'll try to see like scenarios where we observed by Tarun. So he will try to proceed from here.
Okay. Let us go with the everyday scenarios. Just like think like we are scrolling through the mobile device. What actually happens inside? Here we go with the just like watching videos or scrolling through newspapers or any video calls. So let us take an example. Just we are scrolling through any newspaper on the phone. So what exactly happened here is just like the CPU will wake up, and also it will try to render the text and images within that. So that, but here the thing is our memory and input output domain stay constant at the fixed power, which is probably it is wasting that. So coming to this, let us think like we are going on with a video call. So the demand here also, the demand isn't constant, so it will go fluctuate up and down. Just like the CPU will take more whenever the light changes, just like whenever the speaker will changes within the call. So the memory power and as well as the CPU power would not be in the constant way, and it will fluctuate accordingly. So our main goal is simple. Just like whenever the power is low, just like the working, whenever we are working, whether we are doing a light task, the power need to be in the voltage and the frequency that we are sending to that particular domains need to be low. And whenever we are working on the high-end task like gaming or anything, just like video editing, so the CPU would be on the high end, and the memory which are on the low end, it need to be distribute the power to the CPU without wasting on the memory. Let us go with the observations. So main thing is our current systems. Let us say our first problem, fixed power for input, output, and memory domains, so resulting in the energy wastage. So we typically just like we say, we tune our systems for the worst case scenarios, like it's say just like nobody will get short on that power, but it wastes just like a massive amount of energy. The others, like 95% of the time we are not at the peak load, but still the energy getting wasted. And coming to the second one, no cross domain power sharing. Just like the power saved in that memory doesn't automatically help our CPU, because these domains aren't talking to each other, just like they are unable to coordinate each other. So if the memory could have the spare power sitting, which is on the ideal state, while the CPU is just like the CPU is on the high state, it is actually taking much power, but the memory is on the ideal state, we are just wasting the power on the memory rather than giving it to CPU. So basically the memory domain is on the isolated state. So coming to the next one, varying memory demands and resulting over the provisioning. So here, whenever the frequency changes, the interface settings, which are they have the timing parameters in order to control the data into the memory and out to the memory. So these domains aren't talking to each other, right? So the interfacing timings rarely change with it whenever the frequency changes. So we will lose that potential savings, and as well as whenever the latency hits, there would be a penalties, just like we do not the lag and everything. So coming to this, just like at the final thing, the user feels this as a shorter battery life, just like the power would be wasted on the things which we are not even using. And occasionally we'll experience those lags, and also different parts of the chips will fight over that fixed power. Even our mobile devices and the computers will have a fixed power in order to distribute to the whole system on the chip. So coming to the next, the related work. Here, let me clear. So here there's been an excellent prior work on this power management. Oh, so first one, memory scale is memory scale only on the DVFS. So coming to this, reducing memory power whenever it is not heavily used makes sense. But whenever here's the catch, so if you don't reallocate that saved power to whatever it is the bottleneck, just like whenever we experiences those lags, the user sees the little benefit over that. So the power just sits there, and it was unused. So coming to that CPU, next one, that core scale, so which is nothing but the CPU and memory coordination. So it will helps a lot, but especially within servers. So whenever it comes to the mobile devices, like I have input output interconnect to consider, and also the plus very tight thermal constants, how I can say, and mobile workloads shift more frequently, and also it unpredictably that server workloads. So coming to that, and finally no one had that combined multi-domain power budgeting with that interface aware memory tuning. So the gap coordinating all these particular domains intelligently, that's what we are targeting. So coming to the next one, the design challenges. So here we faces about the engineering challenges. So the challenge one, existing system on chip that can't apply DVFS properly across the domains. So here we can't just flip the voltages and clock frequencies recklessly. So we have to drain those traffic and also stabilizes those voltages. So then we need to switch frequencies. Otherwise, it will result in the data lost due to without seeing these clock speeds. So what we need to do it in a fast and safe way. So coming to the next one, predicting real-time bandwidth and latency needs of different domains is tough. So coming to here, predicting demand has to be in the lightweight. So we need a tiny hardware counters that which gives us a strong signal without creating any noise. We can't have a zoo or metrics that overwhelm that decision logic. So coming to the challenge, next challenge, the changing voltages or frequencies for several components at once can be slow and risky, and it might stall the whole chip. So coming to this, which we discussed, that changing on the voltages or frequencies without getting the how much data is transferring and the clock speeds, it would be a very risky thing. And coming to the memory DVFS, so here the challenge is mainly the memory interface timing must track the track frequency dynamically. Otherwise, any memory, just like in the DVFS, may frequency scales at all. So any frequency scaling at all, which will leave massive for performance on that particular table. So coming to the next goals, clearly we have the three goals. So first one, that predict performance needs, so across domains using special hardware counters. So since what exactly it is, we need to have a sense demand across compute, memory, and input output continuously. So then decide within our strict power budget how to redistribute, shift power to the whenever the bottleneck is, or do this in a constant manner, and that need to be adapt within the real time. And coming to the next goal, it need to be distribute power dynamically using a global DVFS mechanism, and that's need to be fast and within a low latency. So while coming to this, we need to pre-compute all the DRAM interface settings for each possible frequency and store it on the chip. So that way switching frequencies become just a fast lookup. So we don't need to recalculate those things. We directly deploy the operations. So the speed would be high in order to access those frequencies. So coming to the next goal, applying the domain specific optimizations to maximize those energy efficiency. So here we are aiming for the hundreds of switches per second. If the workload just whenever the workload needs it. So with zero user visible hiccups like invisible optimization. And that's and all. Here Ravi will take care of the motivation.
Yeah, sure. Yeah, so we'll try to understand like what is the real motivation behind to conduct the experiment on this topic. So the first question arises like why do we even need SysScale? So further to understand, we need to actually try to observe the existing SoC like system on chip, how it's behaving when we try to change the power to one of these components. You can say by default, let's say if I want to decrease the power to memory and increase the power, the same power which bypass to computer, how the system is behaving. So we just need to understand instead of making the domains working at their max power, we try to decrease some component and try to pass it to other component, try to see observe the behavior, and so that how the other is getting affected. So one thing, as I mentioned, we need to make sure that CPU performance should not be decreased at any point of time, because the changing of power with respect to other domains, we need to understand that behavior itself. So that's the meaning. That's the real meaning that we need to make the CPU performance constant, and we try to like change the voltage frequency of input and output and memory. So for this, they try to take two experimental setup. One is like try to make the CPU work at the same speed, like it will try to get its own energy, and if it's possible, we try to divert some of energy from memory or input output control to this CPU and try to understand its behavior. So using the multi-domain DFS setup, they try to decrease the voltages of input and memory to 1.06 hertz. So while decreasing, we'll try to understand if is there any effect to CPU or not. That's the only use case we can understand, so that if it is decreasing the CPU performance, no, then something is going on between the memory. If it is increasing the performance, then we need to understand why it is increasing and how they are performing behind the scenes. So that's what the motivation of this, like conducting this experiment on the architecture. So we'll try to see like what they use. So for this one, they try to use Intel Broadwell processor for this, and we need to understand the workloads here so that we get to know essence of what something will do when you try to apply some like some benchmark workloads. So you try to put the system on some stress, and we need to understand like what is the stress means. So for this, they try to use spec CPU 2006 standard, where it consists of certain number of CPU intensive, memory intensive, or input output intensive tasks, and it will try to test their performance, like how they are behaving when they try to have heavy load on them or heavy load on them. So one is 400 dot Pell bench. It is CPU bound. CPU bound does means like you try to run an operation. That operation mostly demands CPU attention. That means CPU try to do some extensive calculations to try to perform the task. So to perform the task, CPU is more important to frequently try to compute something using mathematical expression something. And then we try to use for that is cactus ADM. It is like memory latency. Memory latency is something, but you want something from memory. It's like the CPU is doing the calculation, but it's not about the calculation. It's about try to fetch some instructions or some memory from the DRAM. So it's a memory latency. So you try to see how much time it is taking to get the information from memory to CPU. That is what this workload is. And the next workload is 447 ILBM, which is memory bandwidth. It's not about how much time it's taking the memory coming to the CPU. It's how much amount of data it is carrying from memory to the CPU in the less amount of time. That's what it try to understand. So remember that CPU is working at the same frequency that what it is supposed to have. but memory voltage is getting decreased here. So we try to mainly see what happens with respect to Cactus and LBM. So we try to see like the observations that they try to got here. So one is we try to see like as I mentioned, like since the CPU, like the input output and memory getting the fixed power, we try to observe like how much change of happened with respect to power with compared with the three workloads. So when you run this processor with decreased frequency for these two domains and same constant voltage for the one single domain, we try to compare this power, energy, performance on most of the cases. So one is power. So the power consumption is like almost certain, like since the power is decreased for the memory and input output voltage, the power is gained for this all the workloads. That means we reduce the power. That's for absolutely for sure. Then the difference comes with respect to consumption of energy. Energy is like like you can say like the amount of power that's running over the time is coming as energy. So the energy for Pell bench is like we save the energy with respect to Pell bench because uh, Pell bench mostly work with respect to CPU intensive task. And then when you try to work so much of on CPU as it's running at their highest speed, there is no like lack of power wasted with respect to memory. So that's why Pell bench is active is fine. But with respect to Cactus area, like the energy is decreased by like let's say almost by 3-4%, because the memory is running slow. Remember that voltage is decreased to the memory component, so the memory latency, like the amount of information passing through the memory to the CPU is decreased. So the CPU is mostly not getting information at the right time. So that's what it makes the energy like the energy is not up to the mark. But with respect to IBM, it's decreased, like it's almost going to negative minus 5%. That means that it's taking so much of energy to transfer the amount required, the information required from memory to the CPU. So that's why, like, since it's not able to get the required amount of energy that it really wants, so that's why it's getting decreased. And we see the negative energy efficiency with respect to LBM. And then with respect to performance, yeah, so pulp bench, yeah, it's not drastically decreased, but yeah, it's okay. Like we can say, like since there is a decrease in the power pump voltage components with respect to memory, it's got decreased. But with respect to Cactus element and IBM, it's drastically decreased. The performance very decreased. That means CPU can't, like CPU can't, most of the like the task is able to decrease the performance with respect to CPU because it's not able to get the information from memory, and the amount of information that it's need to do some specific task with respect to IBM is even more rather a decrease. So the EDP mostly deals with like how the performance and energy combined together. So with respect to this one, if you say like energy is how much of power that you consume over amount of time, and then performance is try to compare like how much amount of task you're doing per time, then EDP try to decides if the energy is using as normal, is the performance increasing or decreasing. So per bench we get the increase of EDP. That means you can able to save the energy, but there's not without loss of performance. That was it really means. And with respect to Cactus and LBM, both are in negative state. So even though you wasted energy, you also wasted the performance. That what really means. So basically you can't simply the output, the main observation you can observe from this graph is even though you decrease the voltage for those domains, that doesn't mean you can try to save energy and try to uh make your system say that it consumes less energy. That doesn't work like that. You maybe you consume less energy, but the performance drastically decreased, and is basically not how you try to perform the system. And the second observation with respect to memory bandwidth. So the third component that we discussed, right? So if you see the memory bandwidth of this one, since 12 bench is a compute based task, it heavily depends upon the computation that try to do on the CPU. So for this, if you see the memory bandwidth, it's asked like the amount of information that required to complete the task is very little. It's almost 0.6 gigabytes per second. So it's not drastically increased at all. But compared to Cactus, it requires like you need to see the y-axis here. So it needs some amount of data transfer constantly between CPU and memory controller. So it's basically requires 4 gigabytes per second. Like the data should be transferred between memory controller and CPU. But if you see the 470 LPM, it's asking very much of amount, 8.9 gigabits of per second data is supposed to be transferred with high bandwidth with respect to memory and CPU. So these are the charts basically shows like how much of like energy that's amount of energy lacking in the memory controller affecting the CPU performance. So that is one other thing. And then the other important information is with respect to like memory performance bound. So this chart, if you need to understand clearly, the 400 Pearl bench is mostly lacking with non-memory component, so it doesn't require any memory here, and it's only slight like slight amount of latency it was facing. But with respect to cactus, it's almost all 90% of the time it's waiting for latency. That means it's always trying to wait for the memory coming to it instead of trying to do some task with respect to CPU. So that's why it's mostly latency bound. And if for with respect to LPM, it's mostly latency. It's not only not getting, it's also bandwidth. It's not about getting sufficient amount of data that's needed for it. It means it need to transfer multiple times whatever the data it requires, so that the CPU is mostly on waiting to reach all the data if necessary and try to do the computation. So that's the reason why LBM is trying like on overall, like when you try to decrease the power for this kind of devices, you need to make sure that the device supposed to work with the specific frequency voltage that is it's getting passed. So that's why we're trying to see these observations. And this is a good observation that we need to remember, that whenever you have whenever any device is working on low voltage, it's not suitable to run them for a longer amount of time. So that we need to remember, because this kind of effects will happen when you try to work on the device, but it's not getting sufficient voltage for that, and it might like harm the devices in the long run. So that's what another thing we need to note. And then the second observation is power use. So let's say let's assume for the first category where you try to do 400 Pearl bench, it is most of CPU bound task. So at that time, memory is not required to work at its worst use case, but it's sufficient to work with the lowest frequency. Then what we observed here is, whenever the voltage is decreased for the memory in the CPU bound task, if you can able to pass not the full budget of that voltage to memory, and you can pass that to CPU, we can like save power. Not only save the power, we can pass that voltage to CPU cores and try to like get more performance gain from that domain. So that's what they observed. So when IO and memory demand is low, then you can just pass that budget to CPU cores and try to increase its frequency from 1.2 GHz to 1.3, and still you can gain the more performance gain. So that's what they observe. Like if we can able to do it with respect to CPU intensive, not memory intensive, but at least in the CPU intensive, if we can able to transfer those energy to it, we can able to get the performance. So that's what the observation 2 is. And then observation 3, like memory bandwidth demands. Now for so okay, all this time we are saying that if you decrease the voltage, yeah, that I know, like the like the performance is getting hit. Now where do you get the memory bandwidth demands? So who demands this bandwidth? How do you know, like how do you know, like who is asking more memory bandwidth device, or like how much CPU is expected for the voltage, and how much DRAM is able to like get the voltage? So for that, they also conducted some experiment to try to understand, like if you can for with different workloads, they try to see like which will demand more memory. So one is like in IO bound and compute are the IO, when you try to connect multiple devices, that's need more memory bandwidth. And then for some compute domains which wants more memory coming, like more information coming from the memory, they need like varying memory bandwidths for the task that they're performing. So this is for sure, like whenever we have IO doing some external devices activity, or else the compute is doing some heavy operations, we require more memory bandwidth. So they try to run multiple computations again, the other benchmarks, to see like how the memory bandwidth changes here. So these are like 4-3 Hammer, A star, and Excellent benchmarks are like those are also in CPU intensive and memory intensive tasks, and they try to see like what is the memory bandwidth that's going to happen. So with HMMER, it's mostly like less memory intensive task, but the memory bandwidth is like it's very high with respect to the starting seconds, and then it is normal here. And then with coming to A star is like it's a famous algorithm where we try to find source destination matching algorithm. It's like Dijkstra other than to A star. So that's the computation that done. So here it's used since it's used heavy graph algorithms, right? So it requires more memory to store the nodes information and try to know the paths and edges weight information. So that's why it is using more memory bandwidth. And with respect to XM benchmark, this is a very high memory bandwidth intensive algorithm. So it prefers so much. And then 3D mark, it's even more. So with this one, what is we can conclude is the amount of algorithm that you run that demands a CPU CPU intensive, which requires more memory more transfers between CPU and memory. Those requires more memory bandwidths. So that's what they are trying to understand. So we need to observe when the CPU is completing heavy task, then we try to observe if it is a memory bound or not based on the data transfer between happening with them. So we need to keep a watch on it, try to see what performance what counters are using all the time, because let's say if you try to store most of the information LLC last level cache, then that will impact your CPU and memory performance. So that's what this observation means. And then we try to go to the this important thing is DRAM configuration. So since till observation 1-2, we are mentioning that the memory is not performing well because of decreasing its voltage. Then what is the reason behind what is the actual reason behind it? It's not performing well. So this is also a point where the previous research box also failed to understand. One is memscale and poscale, because they're also mostly working with respect to CPU bond or only memory bond, original bond, but they try to tune the memory to work with different voltages. They try to fix with certain voltage and try to try to make the memory work at that voltage itself. But dynamically, if you want to change the voltage, what is the one thing that causing DRAM to fail to dynamically adapt to it? So the one observation is using DRAM configurations. So basically, when you try to boot a system, we have two components like SRAM and DRAM. The SRAM component is where try to stores the configurations that DRAM supposed to read, so that it will try to let's say when you try to load a system, the DRAM actually says that I will try to rotate it 1.06 frequency hertz. So whenever you get a clock cycle, it is one complete clock cycle, you try to send the information, and as other clock cycle you try to reach the information. If you try to miss the sync, then it comes clock cycle, you need to wait the DRAM supposed to read at that point of time. So there's a phase of the cycle with respect to original clock reference and the DRAM clock reference. So these settings are called memory reference code that's already stored in SRAM. So this code is part of the BIOS, and where it will try to manages with respect to system memory initialization, and basically it is 1.6 gigahertz. So whenever you try to decrease the frequency of this one, then the ML settings try to says it want to rotate the DRAM at this particular speed, but the voltage coming to it is very decreased. It's not sufficient to do the clock cycle. So if you decrease the voltage, it says supposed to read it. It's supposed the immersive says that you need to rotate at this speed, but the voltage is not sufficient. Then I can't able to rotate. Then it gives a mismatch, right? So that's why the original the cause where decreasing voltage makes DRAM worst performance. So we need to set this MRC configurations at dynamically, so that the memory will try to work at that frequency, and rest of the devices with the single clock frequency, they try to work at the same phase. So that's the fourth observation. So DRAM configuration is very important whenever you try to dynamically change, and you need to get optimal MRC codes values, so that the DRAM will try to refresh and try to work with that. So these are the three from these four observations. The first important thing is we need to make sure that DRAM configuration is optimally fine, and then we try to make sure the power saved from the memory devices should be transferred to CPU, and then we try to see how we can make all these components work together. So that is holistic power management. So that's what the architecture says. We have a power management unit. In the first slide, as I mentioned, the power management is the one that will try to invoke the power budget algorithm, try to make sure how much of amount of voltage is supposed to be transferred between this. And then we have dynamic prediction module. The dynamic prediction module, we try to see is there any heavy workload happening with any of this domain? If some domain is doing heavy task compared to its natural behavior. So that will try to see. And holistic power management is the one that I'm talking about, where you try to understand how much amount of voltage that need to be transferred between the domains and to optimize the work. So if you try to communicate with each of these, like separate domains. So that's what is that. So we try to deeply discuss about power management flow, demand prediction, and holistic power management. So yeah, we'll deep dive into it first for the power management flow. So yeah, so the power management flow works with this one. It's like a step-by-step process. We can just understand it as a pseudocode algorithm. So it's simply we can understand is that one. Let's say you have a black box here that is called demand prediction mechanism. You can understand such a way that we will try to understand in the second step, but this step is prior to this one. So it's a black box. Let's say something say, hey, some domain is asking more power or it's doing so much work. So you need to, it's not able to increase also, it's also decrease. It's not doing up to its mark. We need to decrease the frequency. So demand prediction says continuously suggest to PMU saying that something needs lesser voltage or high voltage. So with this demand prediction, it will try to inform to PMU says that you either need to increase or decrease. So once we get this information, it will try to ask the CPU or any currently serving request to remove them or store them separately, and they want to try to clear the LLC cache, and they stop request going to the memory controller. So basically, you try to block and drain all the existing requests serving currently. So that you don't need to lose them, you need to store them separately so that that frequency change will happen. Then you try to process it again. So first is you try to stop all the interconnect memory controller. If you remember the architecture, we have interconnect that will stop the information to memory controller, and we have LLC that is talking to the memory controller that will stop. So if you cut those two like cycles, then the memory controller will be isolated, not that for to match this frequency. Then the DRAM enters into self refresh mode. The self refresh mode nothing but we need to flush the new MRC ports. I mean, based on the frequency voltage that is supposed to decrease or increase, the new MRC core supposed to inject into DRAM so that it will try to self-configure with respect to single clock reference, like original clock reference. So for this, they try to load the optimized MRC values to memory controller, and we have the analog one and digital one. They try to load into them. So what that means is, hey, the frequency is decreasing for you or increasing for you. So you need to match this clock reference and try to work functional according to that, so that you don't need to wait or do the double work to perform the task. So for that, we use two type of locks here: phase lock and delay lock. So phase loop lock is basically try to multiply the frequency of original clock reference to some amount of time. Let's say you can observe that it's like an oscillator. So if your oscillator, let's say if someone is hitting it at some constant time, you can do multiple oscillations between the time and then again meet at the same point. So that's what the phase lock looks. Let's say if you want to increase the oscillation five times, so if original frequency is 1 second, you try to do 5 iterations in between that. So that was phase lock. You'll try to multiply the phase so that you will do more operations on that. And the delay lock loop is the one, it will try to set the ratio between the original clock cycle to the phase loop clock. So if it is the 1 second is equal to 5 iterations, you need to have that frequency match, right? If it is one, if you're only doing 4, then there's a mismatch. So that's what delay loop lock will try to do. So basically they try to important so that you will try to match with the all other components functionality with your DRAM. And then we try to, both are same. Like if you want to increase, you try to drain out, enter to refresh mode, try to get the new voltage MRC values and load it to the memory controller and try to perform it with your own phase. Or else if you want to decrease, you try to again like if it is decreasing, no, then you try to exit the DRAM and continue to do the operations. So that's what power management flow says. So whenever you try to get a new voltage for your domain, you especially for the memory controller, you're supposed to perform this operation so that the DRAM will match the original phase of the reference clock and it will work with the same voltage. So, and the next will continue with Tarun will be continuing this one for the other models. Yeah.
Yeah. Coming to the demand prediction mechanism. So probably we here go with two estimation methods. Just like the first layer is the static estimation. So think of it as our quick We use the configuration data and as well as the bandwidth tables and known hardware limits to give us as a starting point. So why static first? So here, because it is very cheap, it's cheap and also prevents obvious under provisioning. And also whenever we want to catch the system complexity in the off-guard manner. So and this is important because the static estimation can't track that reality of that mobile workloads by itself. So what exactly it is? So static gives us the foundation, but we need something more dynamic on the top. As we see here the graph, the memory bandwidth for the display, whenever the HD has been increasing, just like when we increase that resolutions, the memory has been increasing as per that. For the 1 HD and 3 HD, and when we go with the 4K, the memory has been strictly increased. And next, coming to the camera, as the frame rate increases, and here the memory bandwidth also increasing itself. And coming to that 3D Mark Vantage for the graphics one, it is probably increasing whenever the graphic model has been increased. So basically, so this static gives us the pretty foundation, and also so we add just enough dynamic sensing in order to make that great decisions without drowning that noise. Yeah. Coming to the next slide. Here the demand prediction on the dynamic, the second one, the dynamic demand estimation. So where we can see here we can see is just like for the dynamic layer, we need to choose our sensors carefully. So we need that performance counters to predict those dynamic input output and memory bandwidth, and also the particular latency demands as well. So for the fewer counters, it means the lower hardware and also there would be a less chance of false triggers. And also the quality absolutely beats that quantity here, so that we select that 15 performance counters which are related to that memory request in those 3 domains, and ran that multiple workloads to prune that selected counters, so based upon the target prediction load. So we are not basically we are not trying to monitor everything, just like we're trying to monitor the particular right ones here. So next, coming to the next slide, the key counters on the thresholding. So from 15 count, just like here we use that counters in order to make those decisions. So from 15 counters, there would be 4 keys, one are chosen for the performance impact. So basically there are 4 performance counters they will use for that, just like a graphic bandwidth demands, and also the next one, LLC, this is the latency one. The CPU bandwidth, which will trace that CPU bandwidth usage. And coming to that one, it will check for the LLC stalls, which are the memory latency bottlenecks. Is there any traffic is stopped in between the highway state? And coming to the input output domain, it will queue that pressure indicators. So simply here, whenever the signals settle back below that band, we gracefully downshift to reclaim that power. And other domain for other domains, or just like whenever we want to save it entirely. So once we know whenever we want to go up or down, so the keys is just like coordinating that all domains under uniform power budgets. Just like if counter value exceeds the threshold, then system needs that high bandwidth and high performance of the DVFS. And coming to the next one. So here the holistic power management. So what exactly it is, the all domains will work together, just like not in an alone manner in the SysScale. So this is the heart of the SysScale, just like a holistic power management, which will estimate the demands of all domains at a time. So every few milliseconds, we do three things. The first one is just like we need to sense and we need to decide, and also we need to rebalance those things. So here it operates those system in two different points, that is the low performance operating point and as well as the high performance operating point. Let's see just like how it works. If compute is the bottleneck and the memory and input output domains are relatively idle, if we downshift those memory and as well as that input output domain, and grant that if we just like if we freed up those power to compute, it will boost that particular CPU or GPU. If the memory pressure rises, if the memory pressure has been raised later, we receive it and we lift those memory frequency while trimming those compute or input output domains in elsewhere, just like it's basically it's what happening is the dynamic rebalancing. So we need to at the end coming to that the rules. So coming to the rules for the high performance operating point, the first one, the static demand. Whenever which is from the connected input output devices, whenever it exceeds a threshold, more just like it's more memory bandwidth is required. If the threshold is greater than the given one, the memory bandwidth, it requires the more voltage and the memory bandwidth in order to move the data within the system. So coming to the graphics domain, is the bandwidth is very limited. Too many LLC misses, just like if a latency has been increased, there would be a high traffic, just like they'll miss the data within that. So, and coming to the CPU cores, so the CPU cores are bandwidth limited. The high, whenever there is a high LLC, queue occupancy, it would make the just like the tracer which is greater than the core threshold. And memory latency bottleneck, it have many stalls in the LLC. And coming to the input output latency bottleneck, so there would be a long pending queue in the input output domain. So if none of these 5 conditions were true, the power management unit will move this particular system to the low performance operating point. So they will always check for these conditions and make the system reliable. And next, coming to the implementation, here that dynamic power management, in the first state, there would be we pass that demand vector and what are the power, the demands of the 3 components, 3 domain components like memory, CPU, and input output domain, and also that bottleneck flags as well as those confidence will pass it to the holistic power management. And next one, it will go with the targeted ops and also with the watching timeout and memory reference codes. So later it will go with the power management execution and the memory input output DVFS control as well as the power bandwidth management. So here it will the memory transition will happen, and here it would be just like the power manage, it would be drained, and also it will check for the whenever just like is there any slowness over the particular domain and shift those power to the domain which are taking less power, just like it will read the memory in a domain whenever it is taking the low bandwidth compared to the CPU. The CPU is requires high one, so the transition will happen and it will the power will shift to the particular end. So coming to this, so the SRAM would be which is tiny in order for the memory transitions. It's about the 0.5 kilobytes, and it will remove that slow and compute whenever we say just like the slow transitions will remove that heavy returning process, and that would be normally happening during every frequency switch here. And coming to the next one, implementation and hardware cost. So how we can say this is one here we how fast we can SysScale switch. So the total time in order to switch between those domains would be, which is very less, the 10 microseconds. It is pretty fast, just like we can see a changing gears in the car, which would be barely noticed at all. And here how we can say, just like there would be a quick sequence time breakdown across the management. Just like coming to the voltage, adjusting the voltage, it would probably take the 2 microseconds. And coming to the clearing traffic from the interconnect domain, it will probably take the 1 microsecond. And for the waking up memory with the fast training, it around take the 5 microseconds. And for the loading pre-saved settings, which is in the timing parameters for the memory interface settings, it will probably take the 1 microsecond. And coming to the firmware and housekeeping task, it takes the 1 microsecond. So basically why it matter is the switch is so quick so that our apps can keep running smoothly. And coming to the next one, so the evaluation methodology. So here testing SysScale on the real systems. So here what they done is they tested this technology on the real systems. Coming to that, they tested on the 2 Intel processors. One is the Broadwell for the early experiments, and another one is the Skylake for the fully SysScale implementation. They pretty done the experiments and compared those transition within that in how the SysScale is working, and as well as how it is making the mission more reliable. So for the testing approach, they first collected this data to understand that particular problem, then run the complete system tests with the SysScale. So when it comes to that, so same Skylake chip with the SysScale turned off versus turned on. So basically how they compared is on the same chip, they implemented they turned off those SysScale system, and on the same chip they turned it on. Probably they compared how it works without SysScale and after SysScale, what are the transitions and how well the power is managed. They particularly seen by this evaluation. So why
Ravi and Tarun, sorry to interrupt. I think we already spent 1 hour. We need to wrap up maybe in, let's say, 4 or 5 minutes. Can you do that?
Yeah, sure, Professor.
All right. Maybe we can jump into, or quickly go over results and then jump to critiques.
Yeah. Just
Ravi, we cannot hear you if you are speaking.
Oh, sorry, I was on mute. Sorry. Yeah. So we try to mostly comparing the results with respect to multiple research works that are already done previously with respect to memscale and CoScale, which basically trying to find the vectors with respect to others and see how SysScale improves it. So if you see we try to run these workloads on those architectures and also ran the same workloads in our architecture and try to see how the average performance increased here. As I mentioned, everything is a task which runs on multiple components, and if you see on an average case, the with respect to memscale, the SysScale performance 5.4 times much better, and compared to the CoScale, it is 2.4 times more better because CoScale works with a CPU, and memscale, since they not work with respect to dynamically workload changes, it took 5.4 times. Like the SysScale improves with respect to dynamic changes in MRC code, so that's why it got improved. And so on an overall, it's 9.2% on an average, compared with all the benchmarks here. And unlike the other methods, the only change you need to observe is because of 5.4 times it occur, the DRAM interface is settings with respect to each power voltage that is getting dynamically. So there's no wastage power, and also there's increase in the performance due to that. And then with respect to graphic workloads, we remember because when you try to do graphic intensive tasks like 3D Mark 06, Mark 1 are also graphic intensive tasks. With respect to all other previous architectures, the SysScale performs well better because the 3D Mark mostly demands CPU because they need to render into the display and graphic workload, so they try to demand more CPU percent. And if you can able to save the voltage power with respect to memory and input output, and it's efficiently transfer that energy usage to CPU, and you can get more performance. So that's why we see performance improvement is very much high with respect to SysScale. And these are the a few values that we try to clear here. And SysScale frees up power from I1 memory. That's what I mentioned, so that it gives you the graphics engine to run or to render the graphics more efficiently. And then the other comparison mostly is it's 5 times more better than the memscale and SysScale. If you see every time it's outsmarts every other other scale, and it will try to improve its performance with respect to that domain. So because of the drawbacks that we see with respect to memscale and SysScale, it able to solve them, and not only solve them, it try to improve it, and it try to make the performance gain for the other domains as well. And with respect to battery life workload, because since I say all these devices work with respect to thermal domain constraint, and it is essential that you need to extend the battery life to save the energy. So with respect to the mobile devices, in most of the cases, when you try to doing some tasks like web browsing, like gaming or video conferencing, the power consumption is become less by this values. So because if you're not allocating the power, you're not now if you're not allocating it's a fixed power budget, you try to scale them on dynamical demand basis. So that's the other important task that you're trying to do. So on the three results, we try to present three important things. One is you try to improve the DRAM configurations, and you try to make them performance better. Second is you try to improve the CPU performance with respect to transferring the power from memory input down to the CPU. And third one is you try to make sure that the energy consumption is decreased, and because you try to dynamically send the voltage, it's not only fixed power algorithm. So the results try to show you the whatever the observation that we did and what are the experiment that we run is a problem. And you do using the demand prediction algorithm and holistic power management, you try to capture the essential voltage required for all the components and passing that essential components to the required components in dynamic phase. So that's why the results actually depicts you more increasing the performance with respect to battery power, memory, and CPU intensive tasks. And the other results mostly deals with the, as I said, the thermal design power. So the entire range of the the devices range of voltage power is only 3 volts to 91 volts. So we can able to increase the power capacity of each device. And due to the different DRAM frequencies, it can able to work with different memory types and support multiple operating points, because operating points nothing but you can try to use it with respect to idle scenario, or you can use it with high usage scenario, or you can use it with low usage scenario. So based on the multiple operating points, the holistic power management will try to increase or decrease the frequency of each device. And the takeaway, SysScale try to adapt with different hardware configuration, based on the hardware configuration that you try to involve. Because since we try to run this experiment in the Intel Broadwell, it's not only to the specific hardware, you can also use this in different hardware configurations. Then for the strengths of the SysScale, so what makes it so special is basically proven with a real hardware. It's not a simulation that we ran, or it's not an observation we did. It's actually we implemented it in Intel Broadwell Skylake architecture and try to get the results out of that. So it's actually proven in the real world. And the transition from low performing point to high performing point is really narrow, because it can able to perform in under 10 microseconds. And then prediction is important, so it can able to dynamically predict because using of the counters, the performance counters, it can able to see the operating point is high or low. And then it's also with the competition, because we have comparison with memscale and SysScale, it can able to give 5 times much performance with respect to the previous architectures. And then the one is it can able to store the pre-stored interface settings, because the DRAM requires the MRC configuration. Once you know what is the set of MRC configuration that already know, you can store it in the SRAM. So that's what the strengths of the SysScale. And the big picture, you can say this solution is complete power management for the small device for mobiles. And the limitations that we observed in this paper is first one is DRAM voltage flexibility, it can adjust, like it can't adjust DRAM voltage at all, like purely depend upon the hardware limitation. That is like depend the hardware that you're using, it can able to predict or adjust the DRAM settings. If they're using the same MRC courses on a different hardware, it might not work. So it tightly somewhat coupled with the hardwares. And then transition complexity, we like we mentioned, like with respect to phase loop lock and delay loop locks, those might in the process of getting block and draining, there might be some small risks where it will try to stall the entire processing chip. And then, as I mentioned, these are vendor specific flows which are tightly coupled. And like since we are only use the benchmarks of normal CPU intensive and memory intensive, let's say if we try to use more intensive tasks, let's say AI tasks, crypto tasks, blockchaining, we don't know like how the prediction will happen. So in the future computation heavy tasks, we might know like how this might behave. So that is one of the intention. So yeah, since you mentioned like no solution is perfect, like SysScale is a huge step forward with respect to daily hour use case with respect to phones. It might be able to provide the solutions as required. And then our final thoughts for this one is like SysScale's like flow explicitly load and optimize MRC values from SRAM at each switch. As we mentioned, like if can able to store them perfectly, it will try to use that MRC value at various frequency changes, load them instantaneously and roam it. It's a like game changing thing because no one tried to implement the till at that point of time, no one implemented this optimized the MRC values at dynamic rate. So that's why it makes special like to like gaining the performance and also using efficient energy. And then it doesn't completely replace the CPU, CPU governance where like the CPU works with respect to P states and it try to allocate the power to that CPU, but still the OS that runs the CPU is the one who is driving that CPU intensive task. So even though if you allocate complete power to CPU, it depends upon the OS that it might be kill the CPU, like it might kill the task at intermediate point of time, or it might suddenly brush the CPU with unknown scenarios. So it's still the OS is the driver for that, but PMU which mostly care about how it performs over a period of time, observing and try to improving. So that's what it does. So that was my thoughts were. And it goes beyond CPU and or memory DVFS. It also included I/O because previously, for the previous research work, it's only core scale or mem scale, but no one actually considered the input output. Like optimizing that part of memory voltage consumption. So the SysScale try to invoke that domain into that architecture and try to have holistic power management. And
Right.
Yeah,
that was very good. Maybe guys, we can take questions now. We can jump into discussion directly. So if anyone has a question, maybe we can take it right now. I see Gahin maybe has a question.
What happens when 3 of the I/O versus CPU versus memory needs higher clock? First question is that. The second question is, since you said authors have done it on real hardware, like how did they do it? Did they had that SysScale hardware that split power based of the requirement that CPU is signaling them? How did that work in real world scenario?
So yeah, the first question, as you mentioned, like if all the 3 domains actually like requires high voltage. So in the starting slide we mentioned like let's say every device is thermally constrained, so it can able to take it needed like it has some limit of this TDP value. So that is the worst case that they can consume. So if every domain requires there's worst case usage, yes, so it can able to get that one because it's not diverting their required energy to others. If they're not working at their highest point, then only we try to divert that energy to that voltage frequency to other domains. So if everyone is trying to get like maximum utilization, they are already at their fixed budget algorithm. So there is no point you can take more energy or suppress some domain, try to give to other domains. So it coming back to like before SysScale itself, like fixed budget algorithm. So I think that's what I think it will do. And the second question you mentioned with respect to, sorry, I really forgot.
How did they do it on hardware? Right?
Hardware, yeah. Correct. So during the paper, they mentioned like like the SysScale is a firmware level code. So they try to use the algorithms of power budget algorithm written in the power management unit. So it's like firmware level. Try to like where we try to mention the demand prediction. They try to observe specific counters when they try to exceed the threshold. So it's like a software, but on a low level hardware embedded systems. So it's kind of a software with firmware level code management. They did it in the power management unit. Yeah, someone raised their hand.
Yeah, I have a question. So how does like SysScale minimize latency overheads when applying DVFS across multiple SoC domains simultaneously?
So that's why yeah, that's a good question actually. So one important thing we need to mention is whenever we say
Maybe Tarun can answer.
Yeah. Could you please repeat the question once?
Oh yeah. So how does like SysScale minimize latency overheads while applying DVFS across multiple SoC domains like simultaneously?
Just like if it applies so the simultaneously, first it will check for the performance counters, whether where the threshold would be required high, and also they will first in the memory configuration interface settings where we represent the timing parameters, right? So there it need to it will pre-calculate the frequency, just like memory rank for the each frequency, and it will store it on the system on chip memories. So whenever they want to access those same frequencies, it doesn't go to the deployment part. It directly fetches from the wherever it is stored for the each frequency. So by that, the latency would be eventually decreased on the chips for the read and write operations and data movements between the all three domains, and as well as the power would be redistributed based upon the demand where the performance counters will actually calculate.
Okay, thank you.
Any more questions? I guess everyone want to run for dinner. Please prepare very delicious hot meal. I see some people running their ceiling fan, some people doing exercise. That's amazing. All right, yeah, last week, if you remember, there was one talk on DVFS, right? And we saw all of us, we saw like how we could leverage or exploit DVFS to steal information from the SoC or the chip or the processing information, right? And today we saw like how we could leverage DVFS to improve the performance, to make things faster. And you can think like how crazy this computer architecture could be. The same thing can be leveraged as security threat. If you want to block it, if you want to prevent users from playing from frequency, voltage, you will lose the performance. And that's would make it really hard always to focus on one thing. There's always trade-off, always. So the being smart in computer architecture is how you do that balance, how you could achieve the best out of this and the best out of that. It's never an easy job. That's why we don't have a single architecture that can fit all purposes. Whenever we want to move to different application, then the architecture becoming really obsolete. All right. Yeah, feel free to send questions to Ravi and Tarun by email maybe, or as comment in the video and so on. So sorry we couldn't continue because we already spent like 1.5 hours just for this talk. All right, thanks everyone for staying until now. Please don't forget to nominate the best talk for today, regardless if it is exceeding the time or not. We're just talking about the quality here. All right, maybe you can stop sharing. I want to take a screenshot actually of the participant. So maybe make sure everyone enable your camera. We can stop sharing the screen. Ready? Couldn't fit on one screen to take twice. That was amazing. All right. Yeah, thank you so much.
We need to smile.
Sorry?
I was asking if we needed to smile for the screenshot.
Yeah, you'll never know what will be your face expression in the picture. Yeah, we'll see you in person next lecture on Thursday. Thank you so much. Stay safe and healthy and warm. Yeah, take care. Bye-bye.